Okay, I think we're good to get started here. Thank you so much for joining. This is the second webinar in Cancor's webinar series. Super excited for this one, looking at the climate impacts of carbon dioxide removal and how we can start thinking about looking beyond just carbon accounting when considering CDR. We respectfully acknowledge the space that Cancor is headquartered in as the traditional territories of Treaty 7, comprising the Blackfoot Confederacy, that's the Siksika, Piikani, and Kainai Nations, the Stoney Nakoda Nations, Goodstoney, Chiniki, and Bearspaw First Nations, and the Tsuut'ina Nation. These lands are also home to the Otempeswak Métis government, Districts 5 and 6. These acknowledgements are some of the beginning steps on a journey of several generations. We share them in the spirit of truth, justice, reconciliation, and to contribute to a more equitable and inclusive future for all of society. Personally, I'm joining from the ancestral territories of the nation's Treaty 6 here in Edmonton. And my name is Carson Fong. I'm the program manager of CDR at the Pembina Institute. I'm super excited to be joined by two experts from Simon Fraser University today. We're all part of the Cancor initiative. Cancor initiative, it's a multi-organization project that aims to assess the potential of carbon dioxide removal technologies to meet Canada's 2050 net zero goal and to identify policy options that could enable sustainable, equitable, and rapid deployment of CDR in the appropriate contexts. It's led by the University of Calgary, but it includes experts from other institutions, like the two me and the speakers are from, as well as the University of Alberta and the University of Toronto. And to me, the coolest thing about Cancor is that it includes such a breadth of disciplines. We have folks from political science and history to law and chemical engineering and geography and geology. And so together, there's a real benefit and advantage in being able to look at CDR from so many different perspectives. This is all made possible by support from Environment and Climate Change Canada, as well as Natural Resources Canada. And so I don't want to do too long of an intro spiel. We'll get right to the meat of it today. We're super excited to have Kirsten and Isabel join us for this webinar. Kirsten Zickfeld is a distinguished professor of climate science at Simon Fraser University. Her research focuses on the effects of anthropogenic emissions of greenhouse gases and aerosols on climate on decadal to century timescales, with particular emphasis on four broad themes: reversibility of human-induced climate change, Earth system response to carbon dioxide removal, carbon budgets consistent with climate targets, and feedbacks between climate and the carbon cycle. She's a convening lead author for the Working Group 1 contribution to the 7th assessment report of the Intergovernmental Panel on Climate Change and served as a lead author of the IPCC 6th assessment report and the IPCC special report on the global warming of 1.5 degrees. Dr. Zickfeld is also a member of the Scientific Steering Committee of the Global Carbon Project. She's an SFU Distinguished Professor of Climate Science. Isabel Dove is a postdoctoral fellow in the Department of Geography at Simon Fraser University. She joined Dr. Zickfeld's Climate Research Lab after completing a PhD in oceanography, which focused on the Southern Ocean's role in modulating atmospheric CO2 on geologic timescales. Her current research involves quantifying the climate impacts of various carbon dioxide removal scenarios with an emphasis on non-CO2 effects on global temperature. Super excited to have you both here. I'll hand it over to Kirsten in just 1 second, and a note for the audience: if you have questions throughout, throw them in the Q&A tab. The chat's disabled, but there's a Q&A tab where you can throw in your questions, and we'll get to them at the end of the whole presentation. Without further ado, I'll hand it over to Kirsten.
Thank you, Carson. I would like to add that I'm joining this webinar from the land of the Squamish, Musqueam, and Tsleil-Waututh people. So as Carson already introduced, the focus of the seminar is on the climate impacts of carbon dioxide removal. We will start by providing some context and setting the stage. And then we will present the effects of carbon dioxide removal on the global carbon cycle and on global mean temperature. And then we will talk about the implications and draw some conclusions for policy. Next slide, please. So why has CDR emerged as a key mitigation option? So the geopolitical context here is the Paris Agreement, which calls on nations to limit warming to well below 2 degrees Celsius above pre-industrial levels and pursue efforts to limit the temperature increase to 1.5 degrees Celsius above pre-industrial levels. And in order to achieve this, the IPCC, which is the Intergovernmental Panel on Climate Change, which is a body of the United Nations that assesses the latest science on climate change, tells us that in order to reach and in order to halt global warming, that is to stop further global warming, we need to reach net zero human-made carbon dioxide emissions, and we need to achieve a decline in the forcing of non-CO2 greenhouse gases. So the essential concept here is that of net zero. Next slide, please. And so many of us have heard that concept, but what does it really mean? So net zero refers to net zero carbon dioxide or greenhouse gas emissions. And it refers to a balance between anthropogenic, which means human-induced carbon dioxide emissions, and human-induced removals over a specified period of time. So here the idea is that if we balance carbon dioxide emissions with an equivalent amount of carbon dioxide removal, then the effects on climate will be neutral. So there will be neither additional warming nor additional cooling. And what we sort of will show in this seminar is that the climate effects of emissions and removals are more complicated than the simple picture. Next slide, please. So maybe to make sure that we're all on the same page, what is carbon dioxide removal? There often is confusion, for example, between carbon dioxide removal and carbon capture and storage. So those are different concepts. When we talk about carbon dioxide removal, what we mean is again human activities that remove carbon dioxide from the atmosphere and store them durably in geologic, terrestrial, or ocean reservoirs or in products. So these activities could be approaches that enhance natural carbon sinks, so enhance uptake of carbon by natural ecosystems, for example, or by the ocean, or it could be engineered systems such as direct air carbon capture and storage that remove CO2 from the atmosphere and then store them permanently in geologic reservoirs or products. And so we already talked about net zeros. In the context of net zero, we need CDR to compensate for residual greenhouse gas emissions. So that is, if we cannot reduce greenhouse gas emissions to zero, then in order to achieve net zero, we need to balance these residual emissions with carbon dioxide removal. However, in the current context where emissions of greenhouse gases continue to increase, and we are falling short of meeting the climate goal of the Paris Agreement. The carbon dioxide is now also considered as a means to achieve net negative emissions. What that means is that we remove more from the atmosphere that we emit into it, so that we have a net removal of carbon dioxide. And that is needed, as I will show in a few moments, to bring down temperature from an overshoot. So as we approach the 1.5 degrees Celsius target above pre-industrial levels, there's a very high likelihood that we will exceed that level. And so if we want to bring temperature down in the future, then we would need these net negative CO2 emissions. Next slide, please. So as a little bit of context, here's a quick primer on the carbon cycle. What you see here, these are the main reservoirs of carbon dioxide in the Earth system. So by far the largest reservoirs is the geologic reservoir, so the sort of the rocks and the solid earth, followed by the ocean, the land, and then the atmosphere, which has a comparably small amount of carbon dioxide. And these reservoirs, they exchange, so even without humans interfering into the carbon cycle, they exchange a large amount of carbon between the land and the atmosphere. So this happens through photosynthesis, or now here in Canada, we're in the fall, so trees are shedding their leaves, and that organic material is then broken down and the carbon released back into the atmosphere. So we have these natural exchanges of carbon between these reservoirs. Next slide, please. And humans are interfering in the carbon cycle by emitting currently around 40 billion metric tons of carbon dioxide per year into the atmosphere. About half of that remains in the atmosphere, whereas the other half is taken up by sinks on land and in the ocean. So currently, sinks do us a huge service because they mop up around 50% of the carbon that we emit into the atmosphere. And so the idea of CDR here is to either enhance these natural carbon sinks on land and in the ocean, right? For example, by planting trees, restoring forests, increasing soil carbon storage, or managing forests differently, or changing agricultural practices, or other engineered methods would then remove carbon dioxide directly from the atmosphere. So this would be the case of ducks, for example. Next slide, please. So what is very important to understand is that once we emit carbon into the atmosphere, it stays there for almost forever, at least from a human time scale. So what this figure here shows is the percentage of carbon dioxide emissions that remain in the atmosphere over a range of different time scales, so from 0 to 10,000 years. And so what you see here, so the first thing is the more we emit, the longer the carbon stays into the atmosphere. But then also, what is very important to realize is that a pretty large percentage, which is 20 to 40% of that carbon that we emit, remains in the atmosphere for thousands of years after an emission. So carbon has these very long-lasting effects on the atmosphere, and then because it is a greenhouse gas, also on climate. Okay, next slide, please. Okay, and this is one reason why, in order to stabilize climate, we need to reach net zero carbon dioxide emissions. And this slide here is an attempt to illustrate this. So on the left-hand side, what you see are carbon dioxide emissions as a function of time. So this is an idealized case where we have, so that this dashed line shows carbon dioxide emissions over the historical period. So we're now, as I said earlier, close to 40 billion metric tons of carbon dioxide. So then let's say that, so we shut them down immediately. So from So today we stop emitting, and this is a highly idealized case, but this would also be true for an emission trajectory that gradually ramps down carbon dioxide emissions. So this is sort of it's the reason I use this idealized scenario is that it's easier to illustrate things, right? And if you look at the middle panel, so the top middle panel, this is the concentration of carbon dioxide in the atmosphere. So what you will see that as soon as we stop emitting carbon dioxide into the atmosphere, concentrations, which is the amount of carbon that accumulates in the atmosphere, comes down. But that is actually then compensated by continued warming, which is due to the slow adjustment of the ocean. So the ocean is very deep in its deepest parts, several kilometers deep. And so it takes the ocean a while to respond to the greenhouse gases in the atmosphere. And this is why, even though the concentration of carbon dioxide comes down, the ocean still continues to warm, and by doing so also warms the atmosphere. Okay, and so then the combination of a declining concentration of carbon dioxide, but this lagged warming from the ocean, then give us an approximately stable global mean temperature, which is shown on the right-hand side. Okay, so this illustrates why, in order to achieve a stable global mean temperature, we need zero or net zero carbon dioxide emissions. Okay, so then going one step further, so then in order to achieve net zero, because again, emissions still continue to increase, and also because there are many sectors that are very challenging to fully decarbonize, we likely need carbon dioxide removal to achieve net zero. Next slide, please. And so as I hinted to earlier, the 1.5 climate goal of the Paris Agreement is now out of reach, and therefore the only way to achieve that would be to return to that target later on. And what the slides illustrates here on the right-hand side is so that the middle panel with the blue lines, these are possible temperature trajectories, where let's say we exceed this target temporarily, and then we come down below 1.5 degrees later on. And on the right-hand side, it shows what the emissions implications are of that. And as you can see, these both curves drop below the zero line, which means that we need net negative emissions in order to bring temperature down from peak levels after overshoot. Next slide, please. Okay, so then to sum it up, what the main takeaways are so far. So the first one is that reaching and sustaining net zero carbon dioxide emissions is required to stop human-induced warming. And the second point is that CDR is needed to achieve net zero CO2 emissions and to recover from overshoot. And I'll pass it on to Isabel. Thanks.
Thank you, Kirsten. So just to reiterate, one of the major goals of CDR is to help us stabilize climate. And so with that in mind, I'm going to explain how CDR impacts climate, beginning with the CDR effects on the global carbon cycle. Next slide, please. So the land and the ocean return CO2 in the atmosphere in response to CDR. So what this schematic is showing is the atmosphere, ocean, and land system. And to summarize or to review what you learned from the earlier carbon cycle crash course is that with a CO2 emission, we're burning fossil fuels from the geologic reservoir and emitting them into the atmosphere. And so this is increasing the size of this atmosphere, ocean, land system. system, increasing the amount of carbon within that system. And the ocean and the land are doing us a big favor in taking up some of that CO2 that is emitted to the atmosphere. And so, but this process goes both ways. So that's a bit of a liability in terms of CO2 removals. So now looking at CO2 removals, when we're removing carbon from the atmosphere back into the geologic reservoir, this shrinks the amount of carbon that's within the land, ocean, and atmosphere, and additionally results in the ocean and the land outgassing CO2 into the atmosphere. Next slide, please. So this is known as the rebound effect of CDR. And so what these graphs are showing is Earth system model simulation data in response to a pulse removal of CO2 from the atmosphere. So a large amount of CO2 is immediately removed from the atmosphere, and then the model is telling us how the land and ocean respond. So looking first at the panel on the left, atmospheric CO2 concentration over a 100-year period, we see that immediately following the pulse removal, there's a decline in atmospheric CO2 concentration, but then it bounces back to levels that are still below the initial concentration, but there is this rebound. If we look at the land carbon and ocean carbon change, we see that the amount of CO2 stored within the ocean and the land is declining over time. So in response to the lower atmospheric CO2 concentrations, both the land and the ocean are releasing carbon back into the atmosphere. So to summarize, CO2 removal is countered by CO2 release from the land and the ocean. Next slide, please. Returning to our idea of net zero, so conventional wisdom would tell you that if we want to balance CO2 emissions and CO2 removals in order to stabilize climate, we can remove tons that are equal to the amount of tons we emitted. But it's actually a little more complicated. Next slide, please. So in order to achieve a balance, this implies that the Earth system effects of a CO2 removal are equal and opposite to that of a CO2 emission. And it turns out that this actually isn't the case due to asymmetry in the carbon cycle. So in other words, the carbon cycle responds differently to removals versus emissions. Next slide, please. To explain this further, so the carbon cycle and climate response to a CO2 removal is not equal and opposite to the response to a CO2 emission. And so this has ramifications for our climate outcomes. To graphically demonstrate this point, so we're taking data again from Earth system model simulations and showing the fraction of CO2 that remains in the atmosphere after a CO2 emission versus the fraction of CO2 that remains out of the atmosphere following a CO2 removal. So looking first at the emission, the slice of the pie that is atmosphere is about 50, it's a little bit greater than 50%. That's the fraction remaining in the atmosphere. Whereas for CO2 removals, that atmosphere slice is smaller. It's a little less than 50% for the fraction that remains out of the atmosphere. So not an equal and opposite response. An important thing to note is that the fraction of CO2 that remains in or out of the atmosphere depends on the climate state at the time of the emission or removal. So the exact slices of this pie can change depending on how much CO2 is in the atmosphere. But the relationship of asymmetry is consistent across climate states. Next slide, please. So to summarize key takeaways of how CDR impacts the carbon cycle, CO2 removal is countered by CO2 release from the land and the ocean. And the fraction of CO2 remaining out of the atmosphere after removal is smaller than the fraction remaining in the atmosphere after a CO2 emission. Next slide, please. So now we'll get into how CDR affects global temperature. And this is important because temperature is the metric that we really care about, and a lot of the negative impacts of climate change are directly related to increases in temperature. Next slide, please. So starting with how CO2 impacts temperature, we're showing results from Earth system model simulations of different pulse removals of CO2, 3 different removals of varying magnitudes. And we're also, the graph on the right is showing surface air temperature change. And so we see that there is cooling in response to CDR, and this cooling is proportional to the amount of CDR. Next slide, please. But that's just considering carbon and removals of carbon from the atmosphere. We know that CDR implementation on planet Earth entails different chemical and biological processes, and these all have Earth system effects. And so in addition to warming or cooling from CO2 emissions or removals, we also have to contend with climate effects from factors like non-CO2 greenhouse gases, aerosols, and biogeophysical effects. So I'll explain each of these in turn. Next slide, please. Starting with non-CO2 greenhouse gases. So non-CO2 greenhouse gas emissions are associated with some CDR methods, and these have the potential to impact global temperature. So, for example, nitrous oxide and methane are 2 examples of potent greenhouse gases that can result in additional warming if they are emitted in association with deployment of CDR. So 2 examples of this. One is bioenergy with carbon capture and storage, or BECCS. So BECCS entails growing energy crops, and this requires the use of nitrogen fertilizers. So if we increase use of nitrogen fertilizers, it's likely that this will also lead to an increase in nitrous oxide emissions. Another example is soil organic carbon storage. So this is a strategy that involves increasing the amount of organic carbon that is stored within soils. And what the figure on the right-hand side of the slide is showing is that when you change the amount of organic carbon within soil, this impacts both the carbon cycle and the nitrogen cycle within the soil. And so this could also cause emissions of nitrous oxide or methane. So right now, these processes are not well quantified. We don't know the exact temperature impacts or the exact amounts of these non-CO2 greenhouse gases that will be emitted, but we know that it is a potential impact on temperature. Next slide, please. Another non-CO2 effect that can impact temperature is aerosol precursors. So the CDR example I'll use to demonstrate this concept is afforestation. So if we increase tree cover with afforestation, this leads to increased biogenic volatile organic compound emissions, or BVOC emissions. So these are compounds that trees emit into the atmosphere. And when these BVOCs are in the atmosphere, they react to form organic aerosols and ozone. And ozone is another greenhouse gas that has the potential to lead to warming. And the organic aerosols could have a cooling effect. So again, the actual climate, or the actual temperature effect is uncertain, but we know that it could impact overall temperature changes associated with CDR deployment. Next slide, please. The final non-CO2 effect I'll talk about is biogeophysical effects. This relates to how changing land surface characteristics influence Earth's surface energy balance, which also impacts Earth temperature. The CDR example used to demonstrate this is enhanced rock weathering, or ERW. So with enhanced rock weathering, different kinds of rocks are ground into a fine dust and then applied on agricultural lands, where they then react with CO2 and draw down carbon. And for this example, I can actually constrain the temperature effect with data. So I received albedo data from a CanCore collaborator, Jonathan Spence, at the University of Alberta. And this data is very useful because deployment of enhanced rock weathering, so spreading this rock dust on agricultural soils, can change soil albedo. Albedo is the fraction of incoming solar radiation that is reflected back to space. So, for example, something that's darker in color tends to have a lower albedo, so less incoming radiation is reflected, and that tends to have a warming effect. You might be able to relate to this in the sense if you wear dark colors on a hot day in the summer, it makes you hotter. Then on the other hand, lighter colored things have a higher albedo, so they're more reflective, and that tends to have a cooling effect. So returning to this albedo data from CanCore collaborator Jonathan Spence, we have albedo data for two different rocks that could be deployed for enhanced rock weathering. The first is basalt, which is this dark colored rock. And the second is wollastonite, which is a light colored mineral. And so we have albedo data for bare soil that has no rocks applied to it, and then also albedo data for each of these two rocks for varying application rates. So we can see that greater application of basalt onto soil results in lower albedo, while greater application of wollastonite onto soils results in higher albedo. Next slide, please. And now quantifying the temperature impacts of these different rocks used in enhanced rock weathering. So I performed 4 different Earth system model simulations, and I'll walk you through each one. And I'm showing the surface air temperature change from pre-industrial, the graph on the left-hand side of the slide, between 2015 and 2100. So the first scenario is a reference scenario in which no enhanced rock weathering is deployed. So we see warming over this 2015 to 2100 period. The second scenario, indicated by the gray line, is the same as the first, except I implemented enhanced rock weathering. So each year, 10 gigatons of CO2 are drawn down by enhanced rock weathering, and this corresponds roughly with application rates of around 50 tons per hectare of farmland. Then finally, the red and the blue lines are representing the scenarios in which I incorporated the changes in soil albedo that are associated with these two different rocks. And so we see that the scenario with basalt enhanced rock weathering is slightly higher than the baseline ERW scenario that doesn't consider changes in soil albedo. Whereas the simulation, the blue line with wollastonite, is cooler. Zooming in on these temperature changes, so the graph on the right, I plotted the difference in temperature for each of the two rocks relative to the scenario with enhanced rock weathering, but no change in soil albedo. And for basalt, we see temperatures that are about 0.02 warmer. And for wollastonite, it's about 0.1 degrees Celsius cooler. So these are small numbers, of course, but for basalt, that's about 10% of the cooling is negated by the decreased soil albedo, whereas for wollastonite, we have an enhancement of cooling by about 40%. So this really emphasizes that biogeophysical effects should be considered in the context of climate and temperature outcomes of CDR deployment. Next slide, please. So this brings us to the idea of carbon versus climate neutrality. And this figure is summarizing the difference between those two frameworks. So on the left, we have a carbon neutral framework, which is this conventional wisdom kind of carbon accounting, where 1 ton of CO2 emitted can be canceled by 1 ton of CO2 removed. But as I've shown, the Earth system responds in complex ways to deployment of CDR. So it's not only the balance of CO2 emissions and removals that we have to consider, but also these non-CO2 effects that could be warming or cooling, in addition to asymmetry in the carbon cycle response to emissions versus removals. And so in terms of policy, it would be ideal to implement this climate neutral framework, which of course then entails more extensive scientific research and better quantification of these effects and investigation into these existing uncertainties. And so to demonstrate differences between this carbon versus climate neutrality framework, we'll present 2 examples of research that's conducted in the Zickfeld lab. So the next slide, please. So here I'm showing results of from SFU master's student Jeffrey Harper. And so Jeffrey conducted Earth system model simulations of a range of different scenarios that implement varying amounts and types of CDR. But importantly, all of these scenarios have the same carbon budget. So between 2020 and 2100, all scenarios have net emissions of 650 gigatons of CO2. Within this suite of scenarios, which again all have the same carbon budget, we have high overshoot and low overshoot scenarios. So high overshoot, there are greater CO2 emissions, so that entails greater CDR. So those are the scenarios that are plotted in red here. And then the low overshoot scenarios are plotted in blue, and they have less CO2 emissions and therefore less CDR in order to achieve this 650 gigaton CO2 carbon budget. And the main point here is that even with the same carbon budget, we're seeing different temperature outcomes. So Jeffrey has highlighted the scenarios that have the greatest temperature difference between them. It's a difference of about 0.05 degrees Celsius. One is a high overshoot and one is a low overshoot scenario. And then they also differ they differ significantly in terms of their land use change over time. So this really emphasizes how land use change and associated biogeophysical changes can have a real impact on temperature outcomes. Please. Now Kirsten is going to take it away.
Yeah, so I'll continue here on with another example. This is from a PhD thesis, and which illustrates a similar point. So what we did here is we constructed a net zero scenario by which residual carbon dioxide emissions are balanced by carbon dioxide removals through large-scale reforestation. And so the way we did this, if you look at the left-hand figure, we have a reference scenario, which is a scenario that reaches 0 carbon dioxide emissions, so full decarbonization by the year 2050. That is that red line, if you look closely. So it hits 0 by 2050, and then it remains at 0. So this is our reference scenario. So now on top of that, we do, again, in an Earth system modeling framework, we implement large-scale reforestation. So we plant trees in areas that were historically deforested. And because of planting trees, we have this additional sequestration, which is illustrated by the green wedge that is shown in the left-hand figure panel. So planting those trees draws carbon down from the atmosphere. So now to build our net zero scenario, what we do is we apply the same amount of emissions that have been removed by forestation as an additional fossil fuel emission. And this is this sort of solid green line, which says baseline emissions plus additional fossil fuel emissions. Okay, so from a design perspective, we apply additional fossil fuel emissions, which are exactly balanced by carbon sequestration in these reforested areas. And yet, then, if we look at the middle panel, what we see is that the concentration of carbon dioxide in the atmosphere differs between our true zero scenario and the net zero scenario, where we offset additional emissions with forest-based removals. And this has to do with carbon cycle feedback outside of reforested areas, which, because reforestation has a warming effect in many regions. There's an outgassing of carbon dioxide into the atmosphere, which causes the carbon dioxide concentrations to be higher than in our reference scenario. And then if we look at surface air temperature to the right, then we see that that difference is even larger, because we not only have a higher atmospheric CO2 concentration, but also have these biogeophysical effects that Isabel talked about, because when we plant trees in agricultural areas, for example, trees have a lower albedo, and this is especially the case in snow-covered regions and mid and high latitudes, where tree mask snow cover, which is very bright. And so, as is illustrated by this green-filled area, these biogeophysical effects contribute to additional warming. So by 2100, so around 2100, even though by construction we have a net zero scenario, we actually have 0.1 degrees Celsius of additional warming. And here I should say, so these are simulations with one single model. There are a number of uncertainties here, which are related to how the carbon cycle responds, and also the exact magnitude of these albedo effects. And therefore, we are confident in the sign of these effects, but not in the magnitude. Next slide, please. So then, to wrap it up, so what we showed is that removing an equivalent amount of carbon dioxide as we emitted may not have the same climate outcome and not achieve the goal of stabilizing global mean temperature. And this is because the net effect of carbon dioxide on temperature is determined not only by CO2, but also by these non-CO2 effects, which is emission of non-CO2 greenhouse gases, emissions of aerosols, these biogeophysical effects such as albedo. And therefore, from a policy perspective, it is very important that these non-CO2 climate effects are taken into account. As I hinted to in my last slide, there are very large remaining uncertainty regarding the quantification of these effects. Excuse me. And for some CDR methodologies, these non-CO2 effects have actually not been quantified at all. So what is needed is additional research to quantify these non-CO2 climate effects of various CDR methods. Okay, so then I'll leave it here and hand it back to Kirsten. Thank you.
Thank you so much, Kirsten and Isabel. That was fantastic. An expansion of some of the work presented at the symposium earlier this year, and really found that ERW albedo effect example quite illustrative of the additional non-CO2 impacts of some of these CDR methods. We've got some time here for questions, so folks feel free in the Q&A tab to slot them in there. I see one already from Tom. If we can share the slides, we should be able to. We'll just have to figure out the best way to do that. But for sure, these are getting recorded and uploaded to the CanCore YouTube page. So you'll get an email about that in the near future after this. As the questions roll in, maybe I'll start with a few from my end. And we collected a few from folks when they registered. Kirsten or Isabel, as we deploy CDR at a large scale, then how much extra CDR might be required to offset the carbon that is re-released from oceans and land systems? Maybe a bit of clarification on that point, please.
Yeah, so I can take that question. So as we said, when we have a carbon emission, about half of the carbon that is emitted into the atmosphere is repartitioned into the land and the ocean. And then conversely, with a CO2 removal, again, about 50% is returned back to the atmosphere from the land and the ocean. And so this repartitioning is about equal and opposite for removals versus emissions. But then we have that asymmetry in the carbon cycle response to contend with. So I briefly mentioned that it is state dependent, but accounting for this asymmetry, it might be on the order of around 10%. A removal is about 10% less effective than an emission.
Got it. Yeah. Thank you. In the closing, Kirsten, you hinted at more research needs to be done to further understand the full climate impacts of CDR. What are some of the key questions you think should be addressed or prioritized with further research?
Yeah, so I would say because of the early prominence of reforestation, forest restoration, and afforestation, there's quite a bit of research that quantifies the albedo effects of those measures. But I would say for many of the other CDR methods, we know very little. So, for example, the results Isabel shared about enhanced rock weathering. So there's very little out there. And there's no Earth system model simulation that really quantifies the non-CO2 effects of this approach. So we need a research agenda that looks. So right now the research is very much focused on potentials, right? What is the sequestration or the removal potential of all of these technologies? But there's relatively little focus on the effects beyond carbon, and they can actually be pretty large. So Isabel showed for enhanced rock weathering that it either enhances or offsets the benefit of carbon sequestration by 10 to 40%. But actually, if we think about reforestation in some regions, so here, especially, as I said earlier, in snow-covered regions, albedo effects can entirely negate the climate benefit of carbon sequestration. And so these, with the original goal in mind, which is to comply with the Paris Agreement climate goal and achieve some kind of stabilization, we need to better understand these non-CO2 effects. And so I would say that's on the science side. On the economics and policy side, I think we need to think about frameworks on how to take these into account. Maybe so again. Because of the prominence of a forest-based project and the voluntary carbon markets, there are some ideas out there how to deal with the albedo effect, right? So some suggest a tiered system where you say, okay, in regions where the albedo effect entirely negates the benefit of carbon sequestration, we should actually not account that as a carbon credit. We can plant trees for many other reasons for biodiversity, ecosystem services, but we shouldn't do it with the climate perspective in mind. And so we could sort of set a threshold where we say, okay, we expect the albedo effect to be be below a certain threshold in order for the for, let's say, forest-based approaches to be considered in those regions. And so we need from a perspective for protocols for the voluntary carbon market, but also for emission trading schemes, we need we need ideas on how we can take these effects into account.
Yeah, perfect. There's a question zooming in, since we're talking about albedo effects. Nazir is asking if geographical latitude has an impact on albedo effects, or if you have any comment or thoughts around how much that impact might be.
You want to take that, Isabel?
Sure. So albedo, the fraction of incoming solar radiation that's reflected. So that is impacted. So the impact of albedo is going to be a function of how much incoming solar radiation there is, which varies by latitude. And also, Kirsten had mentioned snow, and so this is kind of one step removed. But if you have forestation in high latitudes where there's a lot of snow, which has a high albedo, that has a disproportionate effect. The relation to latitude there is where there's snow.
Yeah, so there is so there's a very just to complement this, there's a very strong latitude dependence. So in fact, in the tropics, the albedo effect is relatively small, and what dominates there is the effect of stronger evapotranspiration. Because when we plant trees, the area of leaves increases, and trees also have deeper roots than, let's say, crops or grasslands, and so they can evaporate and transpire more water vapor, which has a cooling effect, right? So the net temperature effect then results from the balance between these competing processes, and in models, what we see that in tropical regions, there's a net benefit from planting trees, considering these biogeophysical effects, which then enhance the benefit from carbon sequestration. Whereas as we move to temperate to northern latitude, that benefit is reduced more and more, and then negated very strongly in some high latitude regions.
Makes sense. Awesome. Okay, one question on policy and international sort of consideration of some of these non-CO2 climate effects. John's asking, are these climate impacts being considered to your awareness by governments or international agencies in policy? And if not, sort of what opportunities do you see for regulators and policymakers to integrate some of these non-CO2 impacts of CDR within policy design?
Yeah, I'm happy to take this one here. I would say some effect are considered. So non-CO2 greenhouse gases, for example, we have this concept of CO2 equivalence, which where we compare the effect of non-CO2 greenhouse gases on radiative forcing to that of CO2, and so we have an equivalence metric which is widely used in policy. It has been criticized because it doesn't work very well in a context where you're trying to stabilize temperature, because of the different lifetime of these gases, right? Sort of if you compare methane to carbon dioxide, they're very different. So in the context of CDR, methane could be relevant when we're trying to restore peatlands. So when we re-wet peatlands, that for some time releases methane into the atmosphere. So you're comparing greenhouse gases, which have very different residence times in the atmosphere. This is why there's a global warming potential for 20, 50, and 100 years, because they compare differently along these different time scales. So there are some problems with that metric, but I would say in most protocols, non-CO2 greenhouse gases are accounted for through equivalency. Other aspects that I would say not so much in international policy, but are considered again in voluntary carbon market protocols as permanence. But again, if we're comparing removal, let's say especially in nature-based removal, where the carbon is stored into biomass and soil, it may have relatively short residence time. Whereas the effect of burning fossil fuels, as I showed earlier, that lasts forever. So it lasts for thousands of years. So we have this discrepancy in time scales. And so one way sort of this sometimes is accounted for is by having some insurance mechanism, so that if carbon is lost from a temporary store, you essentially you have additional carbon credits that you can use to sort of insure those carbon losses. But I would say, and then regarding biogeophysical effect, there are some ideas out there. But I would say, in terms of the international policy framework, these are not yet considered. So here, right, so the key terms are net zero. So this idea that sort of balancing emissions with removals, and many of the integrated assessment models that are used to design scenarios that are consistent with these climate policy goals don't consider these effects such as albedo, permanence, and so on. Yeah, so there's still a need for these to be recognized, and maybe so. Perhaps because we're sort of close to hitting the time. So to me, what this all means, right? Sort of the problem is as burning of fossil fuels. We recognize that we cannot decarbonize or reduce emissions in all sectors, but in most sectors we actually can. So we have the technology, and these net zero frameworks introduce additional uncertainty, right? So from a precautionary policy perspective, the safest bet is to reduce greenhouse gas emissions as soon as possible, and limit the use of CDR to those emissions that cannot be reduced.
That seemed like the perfect key message for us to end off here. Thank you so much, Kirsten and Isabel. This was fascinating and always great. I always learn when I hear you talk. So thank you so much for doing this. And thanks to everyone for joining. Do stay tuned. Check out our website, cancor.ca. Check out our LinkedIn. We will have more webinars coming in the new year. We'll take a little bit of break through December, and we'll be back at these likely in February. So do stay tuned for that. But thanks so much for joining, and I will unceremoniously end the webinar right now.